Hello everyone, welcome back. And this is the second talk for today. And we have Professor Neeldhara Misra from IIT Gandhinagar who will be talking about iterative compression. So thank you for giving this, offering to give this talk, Neil. Over to you now.
Okay, awesome. Thank you so much, Pratibha, and welcome back to everyone. So actually, I was trying to set up the poll that Sakit was talking about to get a sense of if people want to do a branching lecture, and I was also hoping to set it up to maybe ask some questions in my lecture as well. But unfortunately, I can't seem to although I see the poll in the Zoom account, I don't think I can get it started from here for whatever reason. So maybe, excuse me, maybe we can just keep this informal and get the answers from the audience right in the chat. So to begin with, we'll come back to the issue of whether we want a branching session or not, because I think people are still coming back or they're still joining back. So let me just begin by asking, how many of you know 2 raised to k algorithm for vertex cover via any method, but most likely branching, but you've perhaps already seen. So maybe we could just request you to raise your hand if you know of a 2 to the k algorithm for vertex cover. Okay, this is also an excuse to just get some movement going, checking in with everyone. Okay, so at this point, I'm really not sure if a 2 to the k algorithm is going to be news to anybody, going by the response among the participants. So maybe this is going to be like a really quick warm-up. And of course, the point here is not that we are going to get to a 2 to the k algorithm. The point is not either the efficiency, because there are certainly algorithms that run faster than 2 to the k for vertex cover, nor is it to basically make a point about methodology. Here, this is sort of an excuse to get the hang of the whole iterative compression framework. And besides, I think every talk in PC basically has to make a shout out to vertex cover somewhere. So I just want to do my duty right up front, and so we can be done with that. It's of course everyone's favorite example problem. So let's just recall what we have at hand. So so the input is going to be a graph G, and you have a budget to work with, and you want to know if you can remove k vertices so that what remains is an independent set. And in the framework of iterative compression, which is the technique that we want to focus on for the next hour, a little less than an hour, the framework is such that you actually change the problem a little bit and shift your focus to a situation where the input is not just the traditional pieces of input that you have, but you also have something extra. And think of this extra bit of input as sort of a free gift from your best friend or something. Well, okay, if it was really your best friend, they would probably just solve the problem for you. So maybe your next best friend or next to best friend or whatever gives you something that's almost a solution. Okay, so what you have is the graph, and you have your budget, but now you also have a solution that's just slightly off, ever so slightly off. So you have a solution of size k plus 1. And so the solution of size k, or at most k, which is the thing that you're looking for, at this point is still a little bit elusive. But yeah, if it didn't have anything to do, then what's the fun, right? So let's consider this situation, and the question I want all of us to think about for a bit is how best can we exploit a solution of size k plus 1 to get to a solution of size k? What's like the first thing? So I'd like to welcome suggestions in the chat. what's like the first thing that you might want to do with a solution of size k plus 1? Does this, is this extra information completely useless, or can you somehow use it to anchor your search for a solution of size at most k? So I'm just going to pause for like a minute here, and feel free to unmute yourself and make a suggestion as well. I think that should work just fine too. Okay, there's one comment in the chat which says that if the solution happens to be of size of most k, then we are done. That is correct, actually. So vertex cover of size, perhaps if I had said that the vertex cover is of size at most k plus 1, then you could just like, the first thing to do is to check if it's your lucky day and it happens to be of size at most k, and then you can just break open the champagne. Well, okay, maybe not here in Gandhinagar, but just celebrate with your choice of food and drink and call it a day. And in fact, just following up on that really closely is to just check if this vertex cover happens to have some useless vertices, right? So you could check if this vertex cover happens to be minimal. A vertex cover, in this context, I'm going to call it minimal, if any strict subset of the vertex cover is not a valid vertex cover. So every vertex really worked hard to be in this vertex cover. There's a reason that it's there. So in case the vertex cover that your friend came up with is not minimal, then again, you're done, because you can throw something away and you can get to a vertex cover of size at most k quite easily. But let's say that your friend is in the mood to also give you a little bit of trouble while also helping out. So let's say that this does not really apply. So what you have is not minimal, and it's not also size at most k magically. It happens to be a vertex cover that does have k plus 1 vertices. Can you use this to guide your search for a vertex cover of size at most k? So let's name and conquer, maybe. Let's say the vertex cover that your friend gave you, let's call that S star. And you're looking for S, which is a vertex cover of size at most k. Okay, so a couple of comments in the chat already. Others, delete all possible pairs of vertices from the vertex cover, and for each possible pair, try and add all possible vertices. So it's a great suggestion to go by. I'm going to come back to that in a minute. Sohan is saying, if we remove one vertex at a time for the cover and see if it's still a cover. So that's a good point, and that's sort of what you would do to do this minimality check that we mentioned a moment ago, right? So that is, as Adarsh has also commented, that essentially amounts to checking if the vertex cover is minimal. So you're right, we do that. We could do that right up front. Just check if the given vertex cover, once again, let's call this S star, if there is a vertex in S star such that S star minus V is a vertex cover, then we are done. In this case, it's not minimal. But if this does not happen, then can we say that there is no vertex cover of size at most k? So otherwise, what we know is that no proper subset of S star is a vertex cover. So does that mean that we have the license to give up? Does it mean that, oh, because no, nothing smaller than S star is a vertex cover, then maybe the graph just doesn't have a vertex cover of size at most k. Or can somebody quickly come up with an example to refute what I'm just saying?
So you could possibly just take an odd path.
Yeah, an odd path, and I think Saraswati has also pointed that out in the chat. Okay, okay, Mohan also has a generic idea. Two of the vertices of a 3-click in the vertex cover. But from a 3-click, you would need 2 vertices. I'm going to follow up a little bit on what was suggested earlier to work with an odd path. So let's say you have a path on 3 vertices. Say A, B, and C. Let's say your friend gave you this vertex cover, which is perfectly valid. But there is another one which has nothing to do with, which is in fact completely disjoint in this case from the vertex cover that your friend gave you, which happens to be both a smaller vertex cover and not a subset, right? So which tells us that maybe we should look beyond the set S star for an optimal vertex cover. But in some sense, we still want to see if we can squeeze something out of S star, right? Because we don't want to just completely ignore its presence, right? But we do see that certainly ruling out minimality is just like a first step. So either you get an easy win, or the situation is not conclusive, right? You can't really say, oh, let's because a subset didn't work doesn't mean that things are not going to work out at all, right? So so let's think about what can S look like relative to S star. So going back to what Adarsh was saying, delete all possible pairs from the vertex cover, and for each possible pair, try and add all possible vertices. So let's just try to do this with a specific pair, and let's see what you might mean by that. In fact, even before going to pairs, you might say even for a single vertex. Okay, so maybe let me just try and understand what you mean by for each possible pair, try and add all possible vertices. Okay, another idea from Prahlad is check if there exists a vertex in V minus S star whose neighborhood is larger than something in S star. That's very interesting. And okay, I see that a few people still have your hands raised, presumably in response to my earlier question. Your hands might be hurting by now, so you might want to revoke that, so that if somebody is raising a hand to ask a fresh question, then we can distinguish. Thank you so much. Sorry to make you exercise a bit. So okay, so coming back to this. So Adarsh, could you clarify when you say add all possible vertices? I presume you mean that, okay, so you want to get rid of this pair from the vertex cover, and now possibly S star minus this pair is no longer a vertex cover. And the reason for that is that these guys were doing some work, right? So maybe these fellows are like XY, they were covering that for PQR. And if we get rid of XY from the vertex cover, then, and if we determine that we really don't want X and Y in our vertex cover for whatever reason, we really have to pick PQ and R. We don't have a choice, because if we don't, then all of these edges are going to be uncovered, and that would not work. So we traded off. We started with a vertex cover of size k plus 1, and we got rid of 2 vertices. But we actually invited 3 vertices, right? So now we are in fact even worse off than before, because what we're stuck with now is a vertex cover size k plus 2, whereas what we are hoping for is to get to a point where we have a vertex cover of size k or less. So what would be a picture that would, what would be an example that would be nicer? So let's say you're getting rid of a pair. What sort of a pair would lead you to a vertex cover of size at most k? Oh, okay. So Adarsh is saying get rid of a pair and see if you can replace it by a single vertex. So that would be a good situation. A good situation would be when maybe all the edges that are being covered by a pair are incident on only one vertex on the other side. In which case you got rid of two and you added back only one. Which would be a beneficial situation, right? So that's exactly right. Sorry, I kind of probably didn't see through that. So if S star happens to have a pair of vertices whose entire neighborhood outside of S star, right, consists of only a single vertex. So that would be to say, what else could be going on? So X and Y, if they have other neighbors outside of S star, then that's not a very useful pair of vertices to consider throwing out of the vertex cover, because it's going to be at least as expensive to compensate for these guys. So these guys are sort of valuable enough. It doesn't make sense to throw them out as a pair. They could be covering other edges which are inside S star. These edges don't bother us because even when X and Y leave the vertex cover, these edges are still accounted for. So this is not something that we worry about. But okay, so if there was a pair of vertices whose combined neighborhood outside of S star was just a single vertex, then the swap makes sense. What if now you tried all pairs and all of them happen to have more than one neighbor sitting outside? So again, is that a point where you give up, or could you push this idea further? So I'll just repeat the comment that came in the chat earlier. Check if there exists a vertex in B minus S star whose neighborhood is larger than something in S star. So intuitively, it means that maybe you want to know if there's something outside S star which has more coverage power compared to something in S star. So that would give you a way to exchange. So we're really trying to come up with an exchange strategy here. Okay, we could try for triples covered by doubles, right? So we could push this, why stop at pairs, right? So check if there are three vertices that altogether have a neighborhood of size 2 or at most 2 outside. I think there's a comment that supports that now, saying that we could do the same thing for more vertices. So that's exactly where we want to go. So I'm going to say that if you can find any subset of S star, right? Starting with singletons, which was the best for minimality, and pushing that to pairs, naturally leads us to considering the following thought, which is, let's try and see if there is basically a chunk of S star that can be thrown away with an advantage. So I'm going to ask if there is a subset of S star such that the neighborhood of T outside of S star is at most, what do I want to say here? What is it that'll give me a meaningful exchange? Okay. So this is the neighborhood of D in the independent set. So I'm saying n of n of t. I wonder where n of n of t will take you. So n of n of t brings you back to S star, because n of t is not going to have any neighbors outside S star. So I'm curious about what that might mean. But Adarsh is saying basically try to throw them away and replace them by the neighborhood outside. So just try this exchange out. And if that exchange is valuable, meaning that you end up with a vertex cover of size less than k plus 1, less than what you started out with, then it's meaningful to do this, and we should go ahead and do this. And that's sort of exactly right. So I'm going to say less than the size of t. So I want to know if this is less than or equal to t minus 1. Okay, so I'm looking for a subset of vertices in S star whose neighborhood outside of S star is smaller than the size of the set itself. And hopefully it's kind of clear that if you could find such a subset, then you have struck gold, right? Because then you could throw the subset out of S star and replace it with n of t, and you actually have a valid, we have a valid vertex cover. And there's already, as I speak, I realize that what I said wasn't quite true. So maybe somebody can point out why we are not done yet if you can find such a subset. Okay, great. I think others have spoken just as I was speaking as well. This may or may not work depending on whether there are edges that are sitting right inside T. So I think earlier, what I said is that these are the sorts of edges that you don't have to worry about, because even as vertices of T say goodbye to the vertex cover, these sorts of edges are still, they have a backup, right? So there's somebody in S star that's staying back, that's still covering for them. However, if there was an edge that was sitting right here, completely inside T, then this exchange is not going to make sense. Hopefully that's clear. Let me just check in on Mohan's comment. We could construct alternating paths from S star to V minus S star and then see if taking complementary vertices give you a smaller vertex cover. It's an interesting point. To be honest, off the top of my head, I'm not sure. Okay, so basically, you could, okay, so I guess what you're saying is you could try and oscillate back and forth between S star and outside, and kind of see if this set is smaller than the set up there. I guess that's what you might mean by an alternating path. But there may be just a little bit more going on in the sense that these guys that are participating from the S star side in the alternating path may have other neighbors outside S star, right? And so just the action on the alternating path may not be enough to capture whether there is a meaningful exchange. Okay. So just summarizing our observations so far, it seems promising if you have a subset T whose neighborhood outside is smaller than itself, but we have a bit of a roadblock. The plan was that if you find such a subset, then you can sort of swap. So you push T out of S star and you say, you guys, we're done, thanks, but no thanks. And then you bring in N of T to join whatever was left of S star. And what happens is that what's going on between T and N of T is still safe. What's going on between T and S star minus T is still safe. So this new set covers, this new proposed vertex cover covers practically everything. The only thing that's left out that Adarsh has already pointed out in the chat is edges that have both of their legs sitting right inside T. When you push out all of T, these edges get left out. So subsets of S star that have edges sitting inside them are not good candidates for exchanges. So we're basically going to say T subset of S star such that the graph induced on T is an independent set, right? Because these guys are going to move out, and what stays outside the vertex cover must necessarily be an independent set. And of course, it might go and create edges with whatever is sitting outside. That's precisely the neighborhood of T. So we need to welcome them into the vertex cover for all of this to make sense. So to summarize, we could try essentially all possible, subsets of the current vertex cover S star. Let me just write that out. Just zoomed in a little bit. So this is S star. And so by n of t here, I really mean n of t outside of S star, if this is smaller, and no edges in T. Then we do know that S star minus T union n of T is a vertex cover of size at most K. Okay, hopefully this is fair. The only question remaining is to ask if we have really captured all possible scenarios. So, what does the algorithm do? The algorithm is going to try all possible subsets T, and it's going to check if this condition works out. And if it does, it's going to basically stop and celebrate and say, we are done, we have a smaller vertex cover. But if for all possible subsets T of S star, this condition happens to fail either because T has an edge inside it or because the neighborhood is too big, if every possible subset that you try turns out to be unlucky, then then you're just going to say, okay, no, at this point, I truly give up. I give up and I say that there is no vertex cover of size at most K. Is that a fair outcome? So let's analyze both the yes and the no outcomes for this algorithm. So suppose the algorithm says yes. Here we can be quite confident, right? Because just staring at what the algorithm outputs in this situation, which is S star minus T union N of T, it's quite visible that this set is indeed a vertex cover. And why is that? We want to make sure that every edge is covered. And what are the sorts of edges that we have? So if we were to just look at this picture here, there's everything that the old independent set had, which was not in N of T, and then we have T and N of T, and we have a star. So what's essentially happened is that T and N of T has switched places, and therefore all the edges that were going between them are still covered, and T was an independent set, so what's outside is still an independent set. Because in particular, notice that there are no edges from T to the blue set, because that's exactly what's being accounted for by N of T. So hopefully this is fairly transparent, that the fact that the set that we are proposing is in fact a vertex cover. The thing that we may need a slightly explicit argument for is what happens if the algorithm says no. There is no vertex cover of size at most K. Can we be sure that what we have done is exhaustive, that there wasn't a different thing that we possibly missed? Can we be confident about the no answer? The yes answer, I think, is quite visible. What you have, there is a witness, right? You see that what you have is a vertex cover of size at most K. But what if you said no? Then does somebody want to propose a quick argument for why the no answer is also accurate? Again, feel free to unmute yourself if that's easier than typing things out. I'm just going to clean this up a little bit. Thanks for that correction. This label should have indeed been NFT. This is the rest of the old independent set. So it is. Okay, so suppose you use a vertex cover of size k, then we could use t equals s star minus s star intersection u, I think. Yes, quite right. I mean, just S star intersection U, I think, right? There's a follow-up comment. Suppose S1 is a vertex cover of size at most k, then S star minus S1 union S star could have been replaced. All of this, I think, is in perfectly the right spirit. S1 intersection S star, indeed. So we argue this pretty much by contradiction, by saying that, okay, suppose we said no, and suppose we were wrong, that there is indeed a vertex cover of size at most k. Well, let's grab that vertex cover and ask ourselves, well, where does this vertex cover intersect with S star? And of course, it's entirely possible that the intersection of this vertex cover with S star is the empty set, as we see here, which is quite okay. We're going to propose for T to be the intersection of that optimal vertex cover with the given solution S star. And we're going to say that, well, notice that that choice of T must satisfy both of these conditions clearly. So in fact, sorry, I think the comments are right and what I said was wrong. T is the complement of the intersection of the vertex cover with S star. So somebody comes along and tells you, well, okay, here's a vertex cover of size S. So we look at S intersection S star, and that's these guys here. Those are the guys that you retain, and T is everything else, right? So T is S star minus S intersection S star. Sorry, so I think Syriac Uttam, what you have written in the chat is absolutely right. And now working with this choice of T, we see that we must have in our examination of all possible choices of T, we must have indeed hit upon the one corresponding to the vertex cover that is being claimed to be optimal. So I think that's sort of a formal argument, or close to a formal argument for why this algorithm is exhaustive. It is correct on both outputs. And a quick word on the running time. What we have is a vertex cover size k plus 1, so looping through all of its subsets, including the empty set and excluding the full set, because this or maybe the other way around. So essentially, there's no point in retaining all of S star, but you might want to throw away all of S star. That's quite possible. So T might be all of S star, but T wouldn't be the empty set because there's just no point in asking about an exchange in that situation. So more or less asymptotically, the running time is 2 to the k. All the other operations are clearly polynomial time. So okay, so a Okay, so this is the part of the framework that's called compression, appropriately, because you start with a solution of size k plus 1 and you're trying to bring it down to a solution of size k. Let's try to briefly resolve the issue of who gives you this vertex cover of size k plus 1. That did not come out of thin air. So again, any thoughts on how we can start from scratch? So we are solving the original vertex cover problem, and we don't have a friend who's going to gift us a solution of size k plus 1. So is there a way that we can become self-dependent on this aspect? Okay, I'll let you all puzzle that out, but I mean, I'd like you to just, I mean, it's sort of a cute question to think about, but also, um, okay, there's already a suggestion in the chat from Prahlad, who says choose all vertex endpoints. That's kind of close, except that if you choose everything, you start with a solution of size n and not quite k plus 1. And if your starting solution, the gift solution, it's not a function of k, then your compression routine has an unreasonable running time, right? So the goal was to get, the goal, if you like, was to get a order star 2 to the k algorithm. So I want to remove that assumption about having a solution of size k plus 1 to start with only a polynomial amount of overhead. And I also want to make sure that, yeah, S star, um, it would be nice for S star to at least be a function of k, right? Because what you're doing in the compression routine is exponential in the size of S star. So you want to be careful about that. How about taking a vertex cover of, right, Anthony was saying earlier, sorry, I missed that. Okay. Yeah, actually, sorry, I think I'm just scrolling back in the chat. So I think there were multiple suggestions for saying that let's try all vertices to begin with. That's just, yeah, I think that just spoils the dependence here a little bit, but that's very close to what we might want to do. And your suggestion for heuristics is also great, because that just leads me to the idea of possibly working with an approximate solution. So the follow-up comment from Syriac also is about how about we take a vertex cover as small as we get and try to do the procedure repeatedly. So that would be along the lines of starting with an approximate solution, a solution of size at most 2k, for example. That's something that perhaps you have encountered before. But even if not, I think it's easy enough for me to state quickly. So you could start with a maximal matching in your graph, which is easy to find. And if this maximal matching has more than k edges, then you're already done, because any vertex cover is going to need more than k vertices to be valid. So at this point, you can already say no, you don't care. But otherwise, you have a vertex cover of size at most k, at most 2k, by just picking both the endpoints of every edge in the matching. So that's perhaps in the same spirit as some of you were saying, just pick everything. You could do that here, and you have a vertex cover size at most 2k, and you have mostly eliminated the need for your friend, because you could start with this, and you could try to compress it. You could try to go from 2k to 2k minus 1, and then you could reuse this and go to 2k minus 2. I just leave that as food for thought about whether you get to 2k to at most k in one shot, or do you really need to do this reduction by 1 multiple times. So this is one way of doing it. You could kickstart the compressions by starting with an approximate solution. Do keep in mind that here the running time is going to be something like 2 to the 2k, because that's the size of the starter solution. If you really wanted a solution of size k plus 1, you could do what is being suggested in the chat already, but in a confined sort of a context. And maybe I will just briefly talk about that for a minute. So what you could do is pick your favorite subset of k plus 2 vertices in the graph. All right. So you have the entire graph to begin with. And what I'm going to do is say, okay, here, let me find a subgraph of size, I think k plus 2 should work. And notice that H has, as you were all saying, if you picked everything, then H has a easy vertex cover of size. By easy, I mean easy to find. Easy vertex cover of size k plus 1. And that's just pretty much any subset of size k plus 1 would serve as a vertex cover of size k plus 1 for this subgraph. So we are focused presently on just H. And now what we do is we just take the subgraph H and we feed this to the compression routine. Okay, and now one of two things could happen. Maybe the compression routine says, no, there is no way that I can compress your vertex cover of size k plus 1 to a vertex cover of size k. And for example, this might happen if, for instance, you have a clique here, right? If you have a clique, then you already get stuck. But notice that if you can't even compress the solution for a subgraph, then you cannot compress, then even the original graph does not have a vertex cover of size at most k. So this is something that is relatively obvious for a problem like vertex cover, because suppose the whole graph had a vertex cover of size at most k, you could just restrict it to the subgraph and it would work as a vertex cover of size at most k as well. But it does use the fact that the property of having or not having a vertex cover of size at most k is a hereditary property, and it happens to work in this way. There are problems for which this is not true. So for example, for a problem like dominating set, it could be possible that a subgraph has no dominating set of size at most k, but maybe the whole graph is like a global vertex. And boom, suddenly you just have a dominating set of size at most 1. So we have to be a little bit careful when trying to use this trick in conjunction with compression. It really does depend a little bit on the texture of the problem. You want to make sure that it has this hereditary property. But if it does, then this is a pretty, it's a pretty neat sort of trick, which is typically easily adaptable in most situations. So you could say no if the compression says no, but as long as the compression works, what do you do? If the compression worked, then you have a smaller vertex cover now to work with. So so you have a subset right here of size at most k. Now you go to a vertex that's sitting outside and you pull it in and you expand the scope of H to include one more vertex. And this vertex also goes into the vertex cover. And now you have a vertex cover of size k plus 1 again, and rinse and repeat. You keep doing this till, till you finally end up either saying no at some intermediate point or having explored the entire graph, and then you have a solution. Okay, so hopefully that whole framework is now clear. This is the reason why it's called iterative compression, because you kind of repeatedly compress. If you use this method, the one that we described at the end, where you slowly expand on your explored region of the graph till, as I said, you could legitimately say no at some intermediate point, or if you go all the way, then you would have found your vertex cover of size at most k. And I should say that this method can be tweaked to work for problems that are not hereditary as well. I think it has been used, for example, even for problems like connected vertex cover, which is not hereditary at the outset, but it does require, I think, some non-trivial adaptations. But But okay, so this is the overall idea, that you somehow say, okay, what if you magically had a slightly larger solution, a solution whose quality is slightly worse than what you're willing to work with? And the question is, can you use this solution as an anchor to help you to navigate your way through the instance and get a superior solution, get a better one, or can you just rule out the possibility that the graph has a smaller solution altogether? So that's the compression part, and that compression part can be sort of used in a modular way inside, inside this iteration that we just described, and that's something that's the framework that you can apply to multiple problems. So I do realize that I'm not doing great on time, but let's just see if we can think about how one might apply this to slightly more. Well, I mean, this is going to be a less obvious or a less straightforward application of iterative compression. So let's move on to feedback vertex set. So in this problem, we want to identify if there are at most k vertices whose removal makes the graph acyclic. So you're trying to get rid of all cycles. And for feedback vertex set, if you think about, so for vertex cover, if you spend some time thinking about it, there are many branching strategies that emerge that quite naturally take you to FPT algorithms. For feedback vertex set, it's less natural because the obstructions don't necessarily have bounded size, at least not at the outset. The cycles in the graph could be arbitrarily long, and if you were to say that you're going to branch on cycles because that's the object that you're trying to kill, you could get a little bit stuck. This is, as I said, because a priori the cycles may have unbounded length. You could do a little bit of trickery to say, okay, maybe we can do a little bit of pre-processing, right? So there's some things that are very natural for a problem like feedback vertex set. So for instance, if you have vertices that have degree 1, then you could kind of get rid of them, you could delete them, because they never participate in cycles, right? If you have just one neighbor, it takes at least 2 for you to get into a cycle. So, okay, my Zoom UI seems to have frozen. I hope you can still hear me, but okay, now it seems back, yeah.
Yeah, your
Okay.
audio is fine.
Okay, good, excellent. So, all right. So there's already a message in the chat which says, "Can we just focus on killing triangles?" And I will say that there are very specialized situations where killing cycles does come down to killing triangles. So, for example, if you had a tournament, which is a directed graph which is complete, then this would be true. But that's a fairly specialized situation. As you can, maybe the example I've drawn here is misleading, but okay, you can see that there's sort of this 4-cycle jutting out at the top left of the graph that's drawn here. And killing all triangles would probably. Okay, again, maybe it's just a facet of this example, but you can easily think of examples where there are in fact no triangles, but a lot of cycles, and so it's not. And this is exactly the point, that you might be stuck with cycles that are arbitrarily long, and this is going to make things a little bit difficult. But okay, so let me just say that you could not only get rid of degree 1 vertices, which clearly have no roles to play in FVS. By the way, I'm just going to use FVS to refer to feedback vertex set, which is going to be the solution. It's going to be the vertices that you want to delete. You can also argue that vertices of degree 2 also have, in some sense, a limited role to play. Although they can participate in cycles, you can sort of show that you can sort of bypass them. You can short circuit them by just drawing an edge between their two neighbors if there isn't one already. So I'm kind of going to skip trying to argue this formally, but you can either try to work it out as a fun exercise if you don't know, if you haven't encountered this before. But essentially, just take my word for the following. You can get rid of degree 1 and degree 2 vertices efficiently. You can, without loss of generality, be working with a graph where the minimum degree is at least 3. And for such graphs, in fact, you can argue that you can always find a relatively short cycle. And by relatively short, I sort of mean log n-ish, because you could think about, for instance, starting a BFS and sort of realizing that because you're forced, the minimum degree 3 implies that you can't really have like long paths in a BFS exploration, for instance. So it's kind of forced to be a short tree, and you can kind of use that to find a cycle of bounded length. It's still not obvious, given that the length is something like order log n. There is an n in there, but this does lead you to a FPT algorithm, and it's a nice argument based on branching. And there are a few other approaches to FPT algorithms. There are heuristics involving high degree vertices. You could try and argue that somehow it's a good idea to pick. You cannot leave out all the high degree vertices up to a certain point. So that gives you a slightly different sort of a branching strategy. But my point is that finding even a FPT algorithm for feedback vertex status is sort of non-trivial. And this technique of iterative compression leads to, I think for a while, this was the fastest algorithm for FES. And even now, I think perhaps the fastest deterministic ones at least build on these ideas in many ways. So let me just cut to the compression problem. I think here I just had an example of FES, and I'm just going to sort of skip past that just to give you a quick sense of what are we looking at. So I'm going to give you a set S star as before, which is the free gift. It's a FES of size k plus 1. And what remains here, B minus S star, is a forest, right? So every component here is a tree. I'm sort of going to go out on a limb a little bit and say that suppose we have okay, so I'm going to sort of always assume that we have somehow gotten rid of degree 1, degree 2 vertices. We do have to be a little bit careful about this. But again, just in the interest of getting to something of a punchline, let me say that we do something very similar to what we were doing with vertex cover, right? So we kind of guess. So suppose you're looking for S, and so S is the feedback vertex set of size at most k. So what we are going to guess is the guys in S star that don't belong to S. Okay, so these are the guys that we throw out, just like D in the vertex cover example. So these fellows don't belong to the FES that we are looking for. And this is going to be a guess. We are going to try all possible subsets of S star to figure out who are the guys who don't deserve to stay here. And we're going to see if we can work with that to find an appropriate replacement. So all of this is about finding that replacement set. So for vertex cover, it was fairly clear that if you got rid of T, you had to pick N of T. Here it's less obvious because the vertices that we have marked out for removal from S star are vertices that may be participating or killing cycles in all sorts of funny ways. So the point is that we need to take a closer look. But let me start out by saying that the guys who do remain, so this is our view of the world, right? So we're saying, suppose there was a FES of size at most k. Let's think about what did it retain from S star and what did it get rid of from S star, right? So we're going to guess this partition. And just for convenience, let me just say that we throw out the vertices from the graph G. We can sort of throw out the vertices that are in the yes region, because we're going to pick them anyway, right? So let's get them to do the work that they need to do. Let's just throw it out from the picture so that we can just focus on the parts that that we do need to worry about. So essentially, my task boils down to trying to find an appropriate replacement for the no part. But even before getting there, what can I say about the graph induced on the no region? So what should this graph look like? Just like in vertex cover, we said that T must be an independent set. It cannot have edges inside. What can we say about the no part here? What property must it have? Okay, Mohan saying it should be a forest, absolutely, because if there was a cycle in here, there's absolutely no hope of finding a FES that does not pick anything from the no region, because then how are you going to kill this cycle? There's just no hope for this ambition here. So we're going to work with only those subsets of S star which induce forests. And I'm just going to assume that this is S star no, and this is also a forest, therefore. And it's the forbidden forest, if you like. And from the original set of size k plus 1, let's say we removed some L vertices. These are the vertices that we have already picked. So our current budget, so if this is the size of S star, our current budget is like k minus L. We are only allowed to pick k minus L vertices because we have already committed to picking L vertices from S star. Now we are allowed to pick, for the replacement, we are allowed to pick k minus L vertices from somewhere down here. And these are guys that these vertices must be chosen in such a way that they kill all the cycles that are going across these two sets. So remember that you could have two forests, but once you permit edges going across, you could have cycles that go across. And now remember that we have committed to not picking anything from the top. Now we have a budget for how much we can pick from the bottom. And the question is, well, can we systematically identify k minus L vertices from the bottom that kill all the cycles that go across? Okay. All right. So, so now here, okay, let me just make a couple of quick observations. I know that I'm threatening to go slightly over time, but let me, maybe just take a couple of minutes just to get a feel for what's going on here, right? So this was, let's say, a component in our forbidden forest. And let's say that there is a vertex here. That has more than one neighbor into a single tree upstairs, right? Is there something that you can say about this vertex that I'm highlighting down below? And these could be like any two neighbors, but my point is that there's more than one. Do you see a cycle, and do you see a vertex that's uniquely positioned to kill that cycle? Okay, so let me just say that if you have a vertex V down below, which is adjacent to vertices X and Y, which happen to belong to a common connected component in S star, the no part of S star, then, well, because X and Y are in the same connected component, there is a path that connects X and Y that only contains these forbidden vertices, right? And X and Y both happen to be adjacent to V, right? So what I have just described to you is a cycle that has only one vertex in it that you are allowed to pick. So what can you say if you encounter this situation? Is there something that you can do? Yeah, X and Y may be parts of other cycles as well. That's true. But the only thing that I care about for now is the fact that X and Y are participating in this specific cycle, which we are obliged to kill apart from the other things that might be going on. And we also have the knowledge that X and Y are in fact forbidden vertices. So I don't know if this coloring is misleading, but X and Y are vertices from the forbidden region. So we're not allowed to pick them. So we have what, at this point, we have discovered a cycle, C, which is essentially X, P, Y, and this entire path comes from S star, no, and there's V on both sides. Okay, so Aditi has commented saying that V must go into the FES. V is compelled to be a part of the FES, because if we didn't pick V, suppose we didn't pick V in this situation, then who takes the ownership in the FES that we're in the process of building? Who takes ownership for destroying this cycle? Well, it can't be anybody on that path from X to Y, right? And we decided not to pick V. So this cycle, unfortunately, is left untouched. Okay, so now this is sort of going to be a problem, right? So we have to pick V. So essentially, we keep, as long as we encounter this situation, we keep forcing these vertices into our solution. Okay, so V is essentially forced. And so what remains after we are done with this forcing is the fact that every vertex has all their neighbors into different components. Okay, let me just, I realize that I'm kind of way over time here. So I'm going to summarize the main idea from here in a couple of sentences with a clear disclaimer that this is just a hint. It's going to take some work to actually hash out the whole algorithm. But the main idea is to basically say that you either have, sorry about that. Yeah, so you either have vertices that have degree 1 upstairs or degree greater than 1 upstairs. And the point is that both of these situations are in some sense good for you. So if you have a vertex which has, so what we're going to do is essentially start by focusing on the leaves in the forest downstairs. So notice that if you're a leaf, and if you're a leaf in the forest downstairs and you're a leaf in the entire graph, then basically we can just delete you. It's a degree 1 reduction rule. Otherwise, you're a leaf downstairs and you have one or more neighbors upstairs. And it turns out that if you have exactly one neighbor upstairs, then you can carefully do a degree 2 reduction. And if you have more than one neighbor upstairs, then that's kind of cool. So after all your reductions, you come to a point where every leaf has at least 2 neighbors upstairs, and those 2 neighbors cannot be into the same component. And the reason why this is interesting is because now you have a branching strategy on the leaves, and this is the part where this, I think, is gets to a point where it's really kind of creative and interesting. What you can do is essentially say, well, what happens if okay, so maybe I don't want to spoil this entirely. This is a really nice exercise in branching and coming up with an interesting measure. So Saket, I'm not sure if you're planning to do a branching session tomorrow. Then I can try to maybe start by finishing this argument and stealing a little bit of time from there, because I don't want to encroach into the break. And yeah, I mean, do you think that would be a good idea?
Neil, are these people going to have branching?
So I'm not sure. We did not have a chance to poll them, but I'm saying that if we have a branching session, then we can wrap this up there. Otherwise, I can sort of, I mean, I'm not sure how much it's a good idea to continue talking into the break. It's.
I think we should just like, maybe you can just tell the measure and
Okay.
stop there.
Cool. Okay, so then let me try to briefly hint at what's going on here. So so the idea is to basically hopefully some of the things we've said so far are clear, in the sense that we have this situation where what it boils down to is working with a leaf vertex in the forest below. And let's just say that I'm going to say that these leaves have neighbors into more than one components on top. Because when they don't, you can basically handle it. You can apply a reduction rule that kind of pre-processes such leaves. So when you're stuck with these sorts of leaves in the forest below, which have a neighbor in more than one component without having multiple neighbors into one component, because we got rid of that situation as well. We're going to branch on these leaves by asking, do we pick? So let me call this vertex V. Pick V or don't pick V. So if you pick V in your FES, then the size of your target FES, which is K minus L, goes down by 1, because you have just used up a portion of your budget to accommodate V in the solution. So that's clear. That's what happens in that branch. But when you don't pick V, something very interesting happens. So when you don't pick V, what happens is that you can push V into S star no. Okay, because S star no can simply be thought of as tracking those vertices that we are committed to not choosing in our FES. So S star no started out by being our guess from the original solution S star, but there's no harm in repurposing it and using it for other vertices that we have deemed to be unfit for our FES. So in this branch where we say don't pick V, V moves upstairs and it joins the forbidden forest. And in this process, it actually merges two or more connected components. Okay, so the number of components in this forbidden forest shrinks in this branch. And notice that to begin with, you have, like, even if this whole set was independent, remember S star started out being K plus 1. So to begin with, you had at most K plus 1 components. And every time you make one of these moves where you say, oh, we can go upstairs, the number of these connected components actually goes down by 1. So the point is that if at the high level, the intuition I want to convey is that in both scenarios, something is shrinking. In the first scenario, your total budget remaining is shrinking. In the second one, the number of components upstairs, which is also bounded by K, is shrinking. So overall, something like 2K, a total measure of 2K, which is defined as the remaining budget plus the number of components upstairs, this quantity is decreasing by 1 in both branches, whether you pick V or don't pick V. But of course, this branching has to be interleaved with some simplification, reduction rules, and so on. So there is a few details that have been pushed under the carpet. But this is like it's like a really cool branching idea that comes into play here. And this is how you execute the compression. So you keep doing this, you keep cleaning up the graph so that you find these leaves which can lead to some action when they go upstairs. And at some point, when you're done with the branching, you have your answer. If you have a successful branch, then you have a smaller FES. And if not, you can give up. You can give up in this particular choice of S star no. So there's this whole outer loop, which is guessing the no yes partition. So there is that, and there's this branching that goes inside that. And if you do a bit of careful calculation, I think this whole thing works out to being 5 to the K, and you can do even more subtle branching, and I think bring it down to at least 3.6 to the K, which is described in the parameterized algorithms text for those of you who might be interested in that. And yeah, I think in the interest of time, I'm just going to stop talking now because we've kind of 10 minutes over time. So sorry about that. But let me wrap this up here, and I'm around if anybody wants to stay back and discuss this further. But or we could do it, during the break and gather or something like that. But let me stop here. And thanks very much for all your attention and the interaction and the chat. Appreciate it. And thanks, Pratibha.
Thank you so much, Neil. It was great to have you. And thanks to the audience for being around.